Start the recording. All right. So on our Moodle page, I know we're starting 2.1 today. We are? Yes, we are. But to prepare for next week, maybe have a read through 2.1 and 2.2. 2.3 is a case study. And so it's just kind of for fun. Don't worry about, memorizing those or anything. They're just to help you along. If it's helpful, I did post this link to some summary videos. 2.1, we'll talk about this one. Are you typical, kind of the most typical person in the world? They've compiled all this information and determined what the most typical person is looks like. Pretty interesting. But 2.2, 2.3 kind of summary videos if that's what you prefer. But maybe just skim the chapters, even if you're watching the videos. Okay? No worries. So those are just in a little folder. Where did I put them? Oh yeah, and I did, after the fact, post videos for chapter 1, completeness sake. But we've already talked about it, so you did it. And of course, I posted my video. This isn't until next week, so we can't watch it yet. In fact, usually when I try to play it, it's all jaggedy and whatever. So watch it on your own time. But I couldn't find the clip anywhere, so it's actually just me standing in front of my TV recording it because I had to have it. Anyways, the original bootleg, I guess. Terrible, terrible. I do love Superstore though. Okay. What did we do last day? Monday, Wednesday classes are so weird. I feel like we're just getting started and then I don't see you until Monday again. I already miss you. Maybe you feel the same? No? Maybe not? All right. In terms of review, I won't write it down because it was all of last day. But we talked about just variables, right? The most important thing. Okay, fine. Add a page. Oops, that's not what I want to do. All pages. Add a page. But add it up here. Fine, not there. Gonna need some lines, otherwise I'll be all over the place. Just some review from chapter 1, just to get us warmed up, right? And because it's very important, we talked about different variables, right? We had numerical variables, which is whenever we have a quantity, right? So any number, any kind of measured value, speed, distance, why can't I think of more? Age, that kind of thing, right? So any number. And what we said was the prompt that I use is, does it make sense to talk about the average of this thing, right? If it does, then I'm gonna call it numerical. And I'm asleep at the wheel here. Numerical, which is a number. Oh, that looks terrible. Oh well. Does it make sense to talk about the average? I'll put in brackets. If yes, it is a numerical variable. Kind of the extension of that is if I want to report on the average, then I have to treat it as a numerical variable, right? And on the flip side here, we had the categorical variable. And remember, we went deeper, but now that's because we had to see it, right? But at its core, you just need to be able to identify a numerical and a categorical variable, right? And so here, usually categorical, well, always is when there are categories, hate to state the obvious, right? But usually we report the counts in those categories, right? And so we report counts in each category. How many people drive a Honda? How many people drive a Toyota, et cetera, et cetera. Those are categories. What kind of car do you drive? There's only so many things, and you fit in one of those categories if you drive a car. We talked about, so that's what I need you to have from last day today. We also talked about sampling, right? Some good sampling techniques, avoiding bias, that's important, random sampling. And what was the overall goal? Well, the overall goal is to have a sample that's representative of the population that you want to be talking about, generalizing to, right? And so the main way to do that is by randomly sampling. Okay? It's very tempting to go out and say, oh, I need a 50-50 split of males and females, or roughly, and I need this many in this age category and this many in this age category. We can do that, but if we randomly sample, what happens is those are just kind of naturally filled, right? Those criteria. And so it is better to just randomly sample, okay? And so, which is kind of counterintuitive, right? We want it to be representative, but we just trust that that happens by random assignment, okay? And it does. Okay, so today we're gonna talk about summarizing numerical data, okay? And then next week sometime, summarizing categorical data, as you can imagine, is quite boring, right? It is basically just the counts in each category. We can visualize that, right? So summarizing data is often two-pronged, right? We can have summary values, right? Mean, standard deviation, variance, those are probably kind of sort of vaguely ringing a bell, right? Proportions, that kind of thing. Or we can visualize summaries, and that's where we're going to start today. Okay. And so let's see here. 2.1 is summarizing. Wow, that doesn't look like summarizing, but it is there. Numerical data. And in 2.2, we're going to be summarizing categorical data. If you've read chapter 2, you'll notice 2.1 goes on and on and on and on. There's a lot of things we can do with numerical data. And then 2.2 is like, well, here's some things we can do. It's pretty boring stuff. But yeah, so that's where we'll start. Sorry, examining numerical data. But chapter 2 overall is called summarizing data, so not that far off. Last day, we already saw a scatter plot, okay? And so we said, okay, a scatter plot, we use a scatter plot to visualize the relationship often between two numerical variables, right? So already we're just jumping in and looking at the relationship between two variables, and that's great. They've got all these fun kind of bubble graphs. Hey, why can't I click this? What if I have a different tool? Oh, dang. Okay, well, you can go there, gapminder.org, and they have a ton of these different bubble graphs, right? And have you watched a presentation? So Hans Rosling is a famous statistician. He sadly is passed, but he does these very compelling presentations where, you know, he kind of introduced these moving bubble charts, and things are exploding and populations are changing and stuff like that. And they're really fun to watch. It's something to aspire to, I think. But anyways, we'll just work with this static graph that we have here. That's fine. But you can go there and play around, and it's really fun. It's looking at world data, specifically kind of population demographics. Okay. So what we're looking at are things like children per woman. I don't know, how do you say that? Children per woman, they're using that as an indicator of total fertility, okay? And so versus the life expectancy in years, and then it moves through all the different years, and here we're looking at 2011, clearly, as by the background, okay? And so just as a little recap, your X is the explanatory variable, right? So what we're saying is, in this case, we're saying that the total fertility explains changes in the life expectancy, right? And why can we say that? We can say that because we see this relationship. In fact, we see this negative linear relationship between these two variables, right? So here we've got your y-axis, okay, which is your response variable. It's very pleasant. And I'll just put a little recap there that that's the explanatory variable. I guess this is a fun time to say it, but so I don't know how comfortable you are with X and Y axes, right? You're not from the math stream, so I'm not expecting a lot, but I did have a student, I was like, well, it's just the X and Y axis. I don't know why you can't keep track of that. No, I didn't say it like that, but I would never say that. But a student came up to me afterwards and said, I finally figured out how to keep track of them. Okay, so what they told me was that, okay, she just imagines that this here is a tree. Let's make it a Christmas tree. And then she imagines it falling on a little guy, and he's like, no. And that's how she remembered that that was the x-axis. And so that's foolproof. You'll never forget it, right? But so tree is falling there. Anyways, very cute to think about. All right, so back to what we were trying to answer. Do life expectancy and total fertility appear to be associated or independent? Right, that's what we talked about last day, and we said, we already answered this, but we said, okay, because I can kind of generalize this relationship, notice that I'm cutting some of these dots out, right? It's just a general movement, right? We don't have to be super, super specific, okay? And so here, I'm gonna say that they appear associated. In fact, they appear to be linear, right? I can map this by a straight line. I see no other shape that would do a better job, right? And so when I say linear, it just kind of means I could model this with a straight line, okay? And it looks like a negative relationship. And for good measure, we didn't talk about it too much or at all last day, I think. But for later, I would also throw in that it's a strong negative linear relationship, right? And those are the three things that we talk about, right? Strong because first glance, it's obvious, right? There's something going on here. Now we can't watch the video because I ruined the link somehow, but it changed. So if you do go in and watch the video, make sure so when I tried it, I was playing around with it, but you have to change the variables that it looks at. So if you go to that link, it defaults to 2 variables that don't match this one. So you'd have to change it, but you can do that. So here, I'll just say it changed. Take my word for it. Go check it out later. Oh, any questions so far? There are a lot of different graphs and just kind of visualizations that we need to talk about just to check some boxes, okay? But I'm just gonna kind of go through them because we have to. And then once I get to a histogram, then we're gonna talk about that a lot, okay? Because that's the visualization that we're gonna focus on, okay? But it's good to have exposure to all these different visualizations and just know that they exist. First one being a dot plot, okay? And so if you have a GPA, no one less than 2.5, that's pretty good, right? Going to the maximum of 4, wow, what a group. Why did I say wow? Well, looks like there's quite a few people up here. Why? Well, because each observation is a faint blue, and then the darker the blue is, that's supposed to indicate that there are more dots there, right? And so I don't like dot plots because they're hard to read, right? It's hard to know if, try to use this pointer, if this dark blue is the same as this dark blue, for example, relatively the same, right? But it's just hard to kind of see what's going on here. Yeah. If you had to, is this high enough for you guys in the back? I know physics, right? Eye lines and all that. How would you describe the distribution of GPAs in this data set? Now, distributions are something that we're going to talk a lot about, okay? And intuitively, we can already answer this question, right? If I ask you, how would you describe this distribution? Well, I mean, even if you're not feeling super confident, you'd probably start where I started. Well, it looks like GPA goes between 2.5 and 4. Sorry, I should use this pointer. Although it's more fun to do the Vanna White thing. Between 2.5 and 4, right? With a lot of the GPAs kind of hanging around between 3.5 and 4, right? Quite high GPAs, right? And so if you had to build this up, right, what would it look like? Eventually it would look something like that, right? You kind of had to build those up, which is what histograms do for us. And so that's why they're the most common things that we use. But this is one of the ways. And so in general, when we describe a distribution, you have to talk about three things: shape, center, and spread. Okay. And so that's what we're going to introduce terminology for today. So to describe a distribution, I almost did two E's on we. We need to discuss shape, center, and spread. Yeah. So in this case, right, the shape is probably the trickiest one, right? And we don't have the terminology yet. We will. But for now, let's just say that there's very little data up until 3. And then most of the data is between 3.5 and 4, right? We have to do it in words, okay, for now. So I need more space, I think. Oh, well. Few points up to 3, most points, I'll just bump that down for now. Most between 3.5 and 4. Very approximate, right? It's just to give a general idea of what this thing looks like. Okay. How about the center? If you had to, I think you'd want to kind of balance the scale, right? The center should be in the center. So I'd probably put it, and only because I know roughly where it goes, I'd put it around there. How about 3.59? No, it's only because I stole it. So the center is around 3.6. I say around, right? If you said, you know, it's not 3.5. Well, I mean, if you told me it was 3.5, that's fine. But from where I drew the triangle, it's not. Right? If you drew your triangle at 3.5, that's easy. Right? And reasonable too. Right? It's not too far off. Okay. I just happen to know it's at 3.5. Okay. So around 3 points, you know what, just to make it less confusing when you look back at this, 3.5, this insider knowledge maybe is confusing there. But I will add actually 3.59. How about that? Now we're all in the know. But that's okay, roughly. And the spread, try to keep it all on one page here. Nothing precise, just between 2.5 and 4. That's fine, right? Obviously a GPA higher than 4 doesn't exist. And so that's good. Between 2.5 and 4. Okay. All right, dot plots, great. Leading us into shape center spread. So we said if we have numerical data, how we determine that is, does it make sense to talk about the average? Well, if it does, we will probably want to calculate the average. And the average in statistics, we typically call it the mean. I'll use them interchangeably. And in the beginning, I tried to say both, right? The mean or the average, it's redundant, I know that. But the mean is the average. So we'll start calling it the mean instead of the average. But I'll use them interchangeably. Often it's just what sounds better when I'm saying it. There's no rhyme or reason to it. Sometimes it sounds better to say average. Yeah. If we've collected a sample, we can calculate the mean, right? The problem in statistics is that we've got this, okay, so then I have this sample mean, but then if I asked you, well, does the population have a mean? You would say, yeah, of course, that's what I'm trying to figure out what it is, right? And so now all of a sudden we have these two different means and we need notation to figure out which one's which, right? And so what we use, if the mean is from a sample, so if it's a sample mean, we denote it by X bar. Okay, so a bar over the X indicates that X is from a sample, and a bar over it means that I've calculated the mean of a sample X. Okay. So in my sample, in this generic sample, I have X1, X2, all the way up to Xn, okay, which means that a lowercase n is the notation that we're going to use for our sample size. Okay. So here, kind of important, n is the sample size. And if you're reading any sort of papers or publications or even news articles, they'll often report n, right? Lowercase n is the sample size. And it's not important, but a capital N is the population size if you have it. Okay, but we'll leave it there. Okay. So in general, anything with a bar over it. Oh, hello. Yeah. Someone unmuted themselves, I think. Usually that means there's a question. Oh, I should check actually, because I can't see the chat. I'll just double check. All good. Okay, nice. Yeah, heads up. I cannot see the chat if you're in the Zoom room. Okay, anything with a bar over it is a sample mean. We just typically use X for our sample. And then for some reason in upper level statistics, you switch it to Y. Very confusing when you figure it out. Okay, X, okay, great. It's Y all of a sudden. My supervisor had no patience for that. Yeah, whatever, who cares? Making this what? My favorite? Your average smiley face. Okay. So part of the trick here is to keep track of sample information, population information. Population information. Okay. And so the population mean, if you have the entire population, which you will never have, right? You denote it as mu. Okay? Mu is a Greek letter. And if you're, typing these things out, then it's just kind of a fancy M, I guess. But you can type it out as mu. Yeah, and it's got this like kind of fun tail on it. Yeah. Anything from a sample is called a statistic. I know, right? Nuts. Yeah. And so here, any value calculated from a sample is a statistic. Okay. Then they don't have the opposite, but I'll add it in here. I'll just sneak it in here. And any value calculated from a population is called a parameter. Okay. Notice sample statistics, so SS, and then population parameter, so P and P go together, and remember that. So any value from the population is a parameter. So we're going to have this relationship between a statistic and a parameter, right? If I'm trying to figure out what the population mean looks like, what's my best guess? Well, it's probably going to be my sample mean. What am I assuming? That my sample was properly collected and is representative of the population, right? But we have to assume that. We kind of say that we do, okay? And then, so then my best guess at what the population mean is looking at the sample mean. And then we add a little, some buffers there. And then that's statistics. Womp womp. Yeah. Which is pretty funny because when I was doing my master's, everyone would kind of start, so, oh, what are you doing? Oh, statistics. Oh, so you must have all these sports things memorized? What? No, why would I do that? Anyways, that's what people think statistics is. And hopefully you didn't head into this course thinking that. You'd be sorely mistaken. Anyways. Okay. So, but those are sports stats because they're values calculated from a sample. All right. So the sample statistic, like I said, the sample mean, for example, is our best guess at what the population mean is, right? And so what we're going to call it is the point estimate of the population mean. And we're going to introduce that terminology later again, okay? But it's good to kind of see it here and then just kind of keep it in your back pocket. Okay. The thing is, of course, that this estimate is not perfect, right? You wouldn't expect it to be perfect, but you expect it to be close, right? And so that's the idea. Huh? Any questions about that? Oh, well, I guess we should talk about how to calculate the mean. I think we're all pretty good. Hopefully, if I gave you, 4 numbers and I asked you to find the average, what would you do? Add them all up, divide by 4. I hope. Right. And so in general, right, x1 plus x2 plus x3 all the way up to xn, and then divide by n. Right. And so x bar is the sum of all your observations. Oh, hello. Divided by the number of observations. Right. In summation notation, fun to say, fun to do. Or x bar is the sum of x, and maybe to keep it kind of nice and clean, I won't put the subscript or the indices on, but here, this is just shorthand for the summation notation. Fun to say, fun to do. This is your first thing that's going to be on your formula sheet, but I like to put both versions on, right? Maybe you like the summation notation, or maybe you don't. Either way, this formula will be on there, and this one, but you won't need it. You'll just know how to find the average if that's what you have to do. Okay. Back to visualizations. Threw that in there, I guess. Stack dot plot is similar to the original dot plot that we saw, right? The only difference being that all the dots are the same color, so now the shading doesn't mean anything, but we've replaced that with the height of the bars. It's still not that good compared to a histogram, so we're building up to it. But like I said, we're checking boxes here. Of course, higher bars represent areas where there are more observations. This one compared to the first graph, I think this one is easier to read, right? And one thing to keep in mind about visualizations is you should just be able to present them to your client, and they should just look at it and understand what's happening, right? And so that gets lost a lot of the time. You spend all this time, and I'm guilty as well, spend all this time making this elaborate some visualization, but then you have to explain it, and that defeats the purpose. Oh, hello. I don't know. It does make it easier to see the shape, though. We still don't have any terminology for the shapes. But we will. Notice how I'm kind of squinting when I draw this, because I don't want to get too data specific, right? It's supposed to be a generalization that can map to the population. I expect the population where these data points came from to also look like this, right? And so that's why you don't want to get too nitty gritty, right? And jump down here and that kind of thing. You just want to smooth sheet. Or I think it says cooked spaghetti. It's kind of a fun thing. All right, histograms. This is the meat and potatoes. This is what the most common visualization, data viz, as we call it in the biz, but I should spell it out. for numerical data, for one numerical variable. I wonder if I set it to not mute on entry or something. All right. So here is what a histogram looks like. Okay, just in general. The data that we're looking at is the number of hours per week spent on extracurricular activities. Immediately, I'm reacting to this data point down here. It's subtle, but there's someone spending between 60 and 70 hours per week on extracurriculars. Yikes. I need to watch TV sometimes. I don't know. Don't do this. It's crazy. All right. So histograms are similar to those dot plots. It's just kind of a little bit cleaner looking. Okay? But so a histogram shows the data density, right? The higher the bars are, the more data points are there. In fact, here is a count of how many data points are in each bar. Okay? And it doesn't say that, but I'll put it on here. So that's the count. Okay. Now, one thing that's kind of tricky about histograms is we've got these. So these are what we call bins. So there's bins are 10 hours wide in this case. We could have chosen 5 hours, 1 hour, right? We could have changed the bin width and it would have altered the histogram slightly, right? Depending on what the data looks like here. And there's a fine balance between having too many bins and too few bins. I think the next one, okay, yeah, it shows, okay, great. Got an example of selecting the bin width. In general, the default bin width is pretty good, especially if you're using statistical software like or languages like R or SPSS or things like that. Excel is not very good at histograms. I think they just introduced the histogram like very recently, a few years ago, which is nuts. You used to have to make a bar chart, which we haven't talked about, but it's for categorical data, but then adjust the bins so that they'd be next to each other. It's weird. But that's what you had to do. But anyways, so Excel is not very good at histograms, but a lot of other programs are. Yeah? Okay, so those are the bins and the bin width. And like I said, the bin width alters the histogram, right? It's all the same data, but if I do a bin width of what, 45, it looks like here. I've got one bin with most of the data points. There are some here, but this doesn't give me any information, right? This is not good. I wouldn't want to see this. No, thank you. This one would hide too much, right? I would say, so now I'm choosing between these three. Okay. Now, it's only because we can see all three options that I'm gonna say I don't like this one, only because knowing what this looks like, knowing what this looks like here, seeing this makes it look like there's another bump there when there really isn't, okay? So this, I would say, is maybe showing too much, right? The bins here are by 2, it looks like, 1, 2. Yeah, so the bins here are by 2 versus the bins here are by 5. And I would probably prefer to see this one, kind of more general shape. Okay, so here, showing too much detail. Get hung up on that. These, I'm okay with this one. Okay, that's fine. Because if you look at this one and compare it to this one, there's not that big of a difference between the shapes, right? So I'm okay with this one, and this one is great. Right. There's detail, but not too much detail. Obviously, most of the time, I would just give you a histogram, so this is not something that you'd have to decide, right? Or I'll even tell you, use a bin width of this, for example, right? But it's just nice to see the differences and the difference the bin width makes. All right. Are you ready to have some names to these shapes? How am I doing? Good. Yeah. When do we go till 12:20?
Yes.
Okay. Let's see here. If you're in the Zoom room and you don't have a question, make sure you're on mute. I don't think it does it automatically. All right. So, shapes. Just like you know what this shape is, you know what this shape is, you know what this shape is. We're just gonna keep going with those, right? Square, circle, triangle, that kind of thing. We know shapes, right? We're just adding more to the list, okay? Because those will never apply to data. And if they do, it's weird. Okay? But where we're gonna start is talking about modes. Okay? A mode is the most frequently occurring data point. Okay? And so what that means is basically a peak. Okay? And so a single prominent peak or mode. Okay? Our options are going to be unimodal, again, right? It's in the word. Uni means one, modal means mode, right? So one mode, one peak. Okay. Something that looks like this. And remember, we're kind of squinting when we look at these distributions, right? We're not going to get hung up on just a little gap here. And so here, unimodal. If you have more than one mode, you can say multimodal, or if you want to get specific, if you have 2 modes, you can say bimodal, right? 2 meaning, or bi meaning 2. And so here, I just told you to squint in this first one, and then now I'm going to declare this enough of a gap, right? But it is 1, 2, 3, 4 bins. All right, so it's enough. A lot of that is going to come with practice, right? And unless there's a clear choice, right, and you choose something else, as long as you argue your way to it, right? Oh, this is a small data set. So in this case, how I would explain this away, if I wanted to treat it as unimodal, because you guessed it, how many modes you have determines the analysis that you can do, right? So if I want to use this as unimodal, I would say, well, we have a small data set, and if I collected more, I'm sure this would fill out and it would become unimodal. That's sneaky, but I've done it a number of times. Okay. And I think this third one is supposed to look multimodal here. I don't really like calling this two modes here kind of lumped together. I don't think that that's enough space. So how about this? Pretend that there's more space here than what there actually is. And then I would call it multimodal, right? But I disagree, which is allowed. Multimodal. I'll put a little question. Oh, I guess this one we said was bimodal. I just have to assume that's what they want us to see, but I don't think so. And then if there are no apparent peaks, right, if all of them are basically at the same level, what we say is we have a uniform distribution, right? So here, kind of generally, some are higher, some are lower, but if we looked at the entire population, I would expect it to be more uniform than anything else. And so here, uniform. Less. Okay. Oh yeah, so here's the spaghetti. So in order to determine modality, okay, step back and imagine a smooth curve over the histogram. Imagine, this is like an elaborate, imagine that the bars are wooden blocks, nothing else, and you drop a limp spaghetti over them, and the shape of the spaghetti could be viewed as a smooth curve. I just like to say, oh, you should just squint. Don't look too much into it. If we have a unimodal distribution, then we can talk about the skewness. Okay, and so I'll say maybe in green. If we have a unimodal distribution, we can determine the skew. And most of the time, we're going to have a unimodal distribution. And so then the natural next step would be to talk about the skew. Now, the skew, I think, or at least to me as a student, it was counterintuitive, right? Because as humans, we want to talk about the lump of data, right? But in statistics, what we're interested in are these extreme values, these rare values over here. And so when we talk about the skew, it's always going to be skewed in the direction
Bro, there's a dude outside looking at ECUs.
What?
There's a dude on a ladder outside touching ECUs.
A dude on a ladder. Here, I'm just gonna mute all.
Sorry.
There. All right. So we want to talk about these rare occurrences, right? That's what we're interested in. These, where most data points are, that's not that interesting, right? What we're here to analyze are these extreme values. Okay, so in this case, right, unimodal, oh, I shouldn't have made it so lofty, I think. Try again. Better. Unimodal, skewed to the right, right? And so this is unimodal, skewed right. Okay. Oops. So like I was saying, so histograms are said to be skewed to the side of the long tail, so in the direction of the tail. Yeah. And so here, the tail is going to the right. Okay. And that's how you're gonna remember. A little less obvious, but this one I would say is a little bit just slightly skewed to the left, right? So it's unimodal, but it's skewed a little bit to the left, just saying that there's some data points down here more to the left than of the center. So unimodal and skewed left, right? Because the tail is going to the left. We could also say negatively skewed and positively skewed, right? Just whatever you prefer. I'll understand, obviously. And finally, the last one we can say is unimodal and symmetric. Well, and then I didn't draw a symmetric one. There. Nice. The unimodal and symmetric distribution is called the normal distribution. So we're going to talk about that a lot. But we're not going to call it that here. We're just going to leave it at unimodal, symmetric, but that's going to open up a whole bunch of tools for us to use later in our analyses. Probably heard the term outlier before. These are unusual observations, things that we should probably look into. Just make sure they're not data entry errors, which can happen, or it does happen a lot. But like I said, they're also the most interesting for us in our analysis, right? And we have to kind of treat them a little bit differently. Okay? So any unusual observations, right? I would say there is kind of one or two observations. I can't really see the scale here. Around 20 in this case. Now they don't give us what it is we're talking about here. That's totally fine. But just to see it, right? There's, what do you think? If I broke this up I think it's just a height of 1. What am I trying to do? I'm trying to figure out if this is a height of 1 or 2, because that gives me the count in this group. Is that the door? Yeah. Sorry. All right. So here we have one outlier. Have you read the book Outliers by Malcolm Gladwell? It's really good. It's really good. It's like Stats for Fun is basically all of Malcolm Gladwell's books. So I've read a lot of them. outliers is that the one? Yeah, he looks at two relatively parallel people and why was one successful and one wasn't. Bill Gates is one of them, and then he's found kind of a parallel person. He looks at, same opportunities, same kind of circumstances, but one's not successful. Anyways, really fun book. Now I can see that there are probably 3 outliers here, right? 3 outliers. That's quite a few, I think, or just in my opinion, I would probably investigate that a little bit, right? Is there something going on with those 3? One is fine, but when you have a cluster like this, it's kind of worth looking into. How do I know it's 3? Or I'm assuming it's 3, I guess, because I'm also assuming that this is a height of 1 and this is a height of 2, and so together there's 3. Maybe I'll write that. 1, 2, I'm assuming. It's hard to read the scale, but. So those unusual observations, we really want to keep track of those for a number of different reasons. They are interesting, but also they can really affect your values, right? And we'll see that in just a little bit. So now that we have the terminology for these shapes, now how would you describe the shape of the distribution of hours per week students spend on extracurricular activities? Now I would say, with that, I would say it's unimodal. Oops, if I could write. And then it's most definitely skewed because it's not symmetric, right? And so symmetric about the mode. And so it's skewed in the direction of the tail, which is heading to the right. And so it's skewed right. And maybe I'll throw in here, you could say positively skewed. But that just makes it sound like you're emphasizing that it is skewed. It's positively skewed. So skewed right is a little bit more direct. Okay. So now we have terms to talk about these shapes, of course, which is good. Here's a summary of what we saw already, right? But in general, if you're talking about modality, right? How many peaks you have, that's part of it, right? Unimodal, bimodal, multimodal, uniform, right? We saw all those in action. And then the skewness is added to that if it's unimodal, right? And so here so if it's unimodal, then you can talk about the skew, right? Because the unimodal just tells you there's one peak, right? But it doesn't tell you where the peak is relative to the other data. And so that's why we elaborate. Okay. With practice, what you'll find is that there are variables that are just typically skewed. Anything with money is typically skewed. I know it's so unfair, right? Which way is it probably skewed? Probably skewed to the right. A lot of us make this normal amount. Very few make a huge amount, but they exist. Ruining it for everyone else. The skew, I mean. We could have been symmetric, but symmetric wouldn't be very nice either. Then we could have people down here, which I guess is true as well. I don't know. So as a rule, anything with money, house prices, that kind of thing, is going to be skewed, and it's often skewed to the right. But it depends on the scenario, right? But especially being in business, that's good to keep in mind. Okay. What really grinds my gears is most of the time in news articles and stuff like that, they talk about the average home price, okay, which we can't do that. We shouldn't do that, and I'll show you why, but shouldn't do that. Huh?
Especially with Canada wide. That's
Yeah. Yeah, all in one, throw them all in one pot, see what happens. Just even. All right, so which of these variables do you expect to be uniformly distributed, right? No peak, just all the observations just kind of span some range, but there's no reason for there to be few for some values of X. So, sorry, for some explanatory variables, it's just going to be the same. Okay, so weights, I would say, are not uniformly distributed, right? Weights follow, spoiler alert, weights tend to follow a normal distribution, a unimodal symmetric distribution, just typically. Salaries, well, I just said salaries. Typically, I would expect to see something like that. Most people having salaries over here, and then very few over here. House prices, same thing, prices. Kind of, yeah, just generally, you can poke holes in this, but I would say generally like that, right? Most homes are in this range, and then there's some higher end homes. But there are inexpensive homes too. Yeah, I know that. Just in general. Which leaves me with birthdays of classmates, the day of the month. Okay. You heard the birthday problem? The birthday problem is a sort, it's not a phenomenon, but it's at the door. Yes. Where you need a relatively small sample for 2 people in the room to have the same birthday. It's weird, right? But I'm April 30th. Does anyone have April 30th birthday? No takers? Me and the King of Sweden celebrate on the same day. And it also happens to be a holiday in Sweden. And May 1st is a holiday. Us that. Should have stayed in Sweden. But what we would expect, right? There's nothing that says, oh, well, born on the 1st, yeah, just like the rest of them, right? No one says that. Or born on the 30th, well, classic. Everyone's born on the 30th. We don't say that, right? And so that's why we expect it to be symmetric. So, uniform. Uniform is symmetric, but that's not the question. Expect to be uniformly distributed. And so, of course, this one. Okay. We've already sketched some expected distributions, and you can think about these, right? Number of piercings. I don't know. I actually don't know what to expect. You'd have what? 0, 1, 2, 2.5. No. 3. I guess if it's grown over